Good morning, precalculus class. Today you're going to learn about something called the eccentricity value of a conic section. Let's start with the warm-up. Go ahead and pause the video. Try this warm-up. What you want to do is complete the square on it, identify which conic section it is, and all the key information you need, and then draw a quick sketch of it. Go ahead and pause the video now. Okay, so as you can see, you know it's a hyperbola because the x squared term's coefficient is a positive 9 and the y squared term's coefficient is a negative 25. When those coefficients are different signs and they both exist, you know you have a hyperbola. Once we go through completing the squares, I end up with a negative x plus 3 quantity squared over 25 plus y minus 1 squared over 9. So I switched that order so I can clearly see that the y squared is the positive value and the x squared is the negative. This means it is a vertical opening hyperbola. That means it's opening, the curves are opening up and down. Okay, so now let's identify some key information. We know that the center is at the coordinates of negative 3 with the x term and positive 1. We also know that the a squared value is 9. It's always under the positive term, so a is 3. B squared is 25, so b is 5. And if we know a and b, we can then find c, because c squared equals a squared plus b squared in a hyperbola. And let me just move this up a little bit so we can draw a picture. And to finish this calculation, c squared equals 25 plus 9. C squared is 34, and c is the square root of 34, or just under 6. Okay, so now we'll draw a graph of the hyperbola. We're going to draw a little coordinate plane right here. And the first thing we're going to plot is our center point. Make a point there, even though that's not even on the hyperbola. Then we're going to walk the a value up and down since it's a vertical hyperbola, since the a value goes under the y. And the b value is going to be right and left. And this one is wider than it is tall, which is just fine. And we're going to create a box. This box, the corners of it, is where the asymptotes will cross through. And the asymptotes help define the shape of the hyperbola. So this is a vertex, this is a vertex, and this is the center. So right now I'm going to draw in, without a ruler, the best asymptotes I can. They go through the corners of the box. And then let's just pick a new color so we can really see it. And we have our hyperbola. It's vertical, so these curves are approaching the asymptotes, but they'll continually get close to them, but they'll never cross them. So it's a pretty wide opening hyperbola. The other thing I can plot is I can plot the focus points. So we know if the center is at negative 3 for x, and then it is up 1, the focus points are the center plus or minus the c value. So that's where the focus points are. And that's, like I said, was about just under 6. So let's see, that's up 3, 4, 5, 6. So here is a focus. And likewise, 1, 2, 3, 4, 5, 6, just under that is a focus. And that is another great example of a hyperbola. Okay, so today we want to talk about something called the eccentricity of a conic. This is just a value or a number that uniquely characterizes the shape of the curve. So each of the 4 conic sections has a different eccentricity value. And just to kind of help you remember them, I didn't quite put them in the order I'd prefer, but your circle is always an eccentricity of 0. And then as it turns into the ellipse, think about like if you held a flashlight to this surface straight on, you have a circle. And as you tilt that flashlight away from the plane, that intersection or cross section of the cone of the flashlight with the plane changes the shape. So then you turn it into an ellipse comes next. Now ellipses can be very circular or could be very long and skinny. So ellipses have different shapes. They're all, closed ovals, if you will, but they can have an eccentricity anywhere between 0 and 1. So it could be 0.2 or it could be 0.8. So the closer it is to a circle, the closer it is to 0. And the closer or longer that ellipse gets, the closer it is to 1. And you find this by calculating the C divided by the A value. So that is a ratio of C divided by A. Now, if you remember in the ellipse, the A is the longest value. So C will always be less than A, and that's why that ratio of C over A is less than 1. Okay, next, as soon as you release the flashlight, if you will, from the edge of the flashlight from the plane, you get your parabola shape. And the parabola shape is a fixed value, the eccentricity for it. It is 1, so it's kind of next in the sequence. So you start at the circle, you turn that flashlight a little bit, and you get your ellipse, and then you get your parabola. So that's a fixed number of 1. And then lastly, you get the hyperbola. So the hyperbola is when your flashlight is almost parallel to the surface of the paper, or the screen in this case, and that is a value greater than 1. So once again, the hyperbola can have different shapes because the eccentricity can be 1.2, 2.4, like that would probably be a very strange eccentricity. It'll be just a little bit bigger than 1. But it's also found by that same calculation C over A. But remember, in a hyperbola, C is the largest number, so C is greater than A, and that's why that ratio will be bigger than 1. Little note here that helps you think about the shape of a parabola. So we think that 2x squared and x squared have different shapes. They're both parabolas because the former one, 2x squared, is a skinnier or more narrow parabola, but they're really considered the same shape with the same eccentricity, and it's just a matter of one curve is viewed twice as far away. So it's kind of like shrunk and then enlarged. And that's what your 2 is doing. That's a vertical stretch. All right, we're going to use the eccentricity in some problems on the next couple slides. Okay, in the first example, we're asked to write the equation and graph the conic that has an eccentricity of root 5 divided by 3, a center at negative 2, 5, and a covertex at negative 2, 1. So the first thing we can identify is which conic this is. And we know it is an ellipse because root 5 divided by 3 is less than 1. So it is an ellipse. And what I think I'll do to help figure out kind of the rest of the information is I'm going to draw a sketch of this ellipse. So the center is at negative 2, 1, 2, 3, 4, 5. And then it has something called a covertex. Now we're used to vertices, but a covertex, what's that? Well, in the ellipse, a vertex is along the elongated side. So it's the 2 points on the elongated side. Well, the covertex is on the shorter side. So we know that this value right here, negative 2, 1, is kind of the short side of the ellipse. So we don't know how long it is yet, but we know that the minor axis, or half of the minor axis, the semi-minor axis, or B value, is the distance between 5 and 1. So we know that B equals 4. All right, let's write down what we know so far. So first of all, since the B value is vertical, we know this is a horizontal ellipse. So it's going to be x plus 2 squared over a squared plus y minus 1 squared over b squared, which is 16 equals 1. So we're just missing a squared, and then we have on our equation. Well, we know that c over a equals root 5 over 3. And it may be that c is root 5 and a is 3, you know, that it's just kind of an equal multiplier, but we don't know that until we actually figure out what c and a are. So we have a relationship in an ellipse. A squared equals b squared plus c squared. So let's see, I'll just solve this for c in terms of a. We know that c equals a root 5 over 3. So a squared equals 16 plus a squared times 5 over 9. And we can subtract that. So let's see. A squared minus 5/9 a squared is 4/9 a squared equals 16. So a squared equals 16 times 9/4. And a squared equals, let's see, 4 goes into 16 4 times. And you get 36. So a is 6. All right. If a is 6, we know our equation, because a squared goes right here, and that's our equation. We can also finish drawing our ellipse, which I'll do in a minute, although I'm going to run out of space. And we can also find c then, because c over 6 equals root 5 over 3. So clearly c equals 2 root 5. And that's the distance to the vertices. Okay, let's just finish drawing this ellipse. So I'm going to go 6, the a value, in both directions. Place little x's. I need to go up 4, my b value, so I'm just going to do it right over the word. Sorry about that, guys. And then I'm going to go left 6. And a little x there. And I think I'll take a new color. And we will graph this ellipse. There it is. So I went 6 left, 6 right, 4 down, 4 up from our center. So there's a lot going on here. The key that might have been hard is knowing covertex is giving you the b value. Once you have the b value, you almost have your equation, but you've got to find your a value. So you had to use your value of your eccentricity and your relationship between a, b, and c, and use that system of equations to solve for what a and c are. All right, that was the first example. Let's look at another one. All right, so we have one more example. Let's take a look at this. So here's the equation in general form of a conic, and the first thing we want to know is what kind is it? So I look at my coefficients, and I have a coefficient of x squared of 4, and a coefficient of y squared of 9. Those are the same sign, so it's not a hyperbola. They're not equal, so it's not a circle. This is also an ellipse. Just happens that I had 2 ellipse examples. So now the question is, what is its eccentricity? So in order to answer that, I need to complete the square and figure out my c and my a value. I know its eccentricity is less than 1, but I need to actually find those values. So we are going to complete the square, put it in standard form, then we'll answer what is its eccentricity, and the last thing we'll do is answer whether these points are on it or not. And we could do that through graphing, but we'll also do it algebraically. So why don't I pause the video here, you try to answer those or complete the square on your own, and then we'll go over it together. All right, so here is the equation of this conic. So it's x minus 2 squared over 9 plus y minus 2 squared over 4 equals 1. But what this tells us that it is a horizontal ellipse. We know it's horizontal because the x term has the largest value underneath. And we know that a squared is 9, or a is 3. B squared is 4, so b is 2. I can now calculate c value. So we know that a squared equals b squared plus c squared in an ellipse. So we have 9 equals 4 plus c squared. C squared is 5, and that means, go this way, c is the square root of 5. Once I know c and a, I know that the eccentricity equals c divided by a, which is root 5 over 3. That is our value that defines the shape of the curve. Okay, the last question we have to solve are these points on the ellipse? Well, they're on the ellipse if they satisfy this equation. So all you have to do is plug in these 3 ordered pairs into the equation and see if they work out. Well, the first one's really easy. If I plug in 2, 2, 2 minus 2 is 0. And so that's 0 plus another 0, and 0 does not equal 1. Well, what's that telling you is the center is not on the ellipse. So this is a big no. Now we just have 2 more points to figure out. If you want to pause it here, you can and try it on your own. Otherwise, I'll just let you know. If you plug in both of these ordered pairs into the equation for x and y, both of them end up becoming equal to 1. And so these are both yes points on the ellipse, or on the curve of the ellipse. All right, that's the last question. Using eccentricity or answering questions about eccentricity of conic sections, go ahead and try your homework.